Welcome to our fifth video on projectile motion. All of our stuff on projectile motion has come up to this one, and this is the trickiest type of problem that we can run into, or at least the longest type. In this case, we have a projectile that is not landing at the same height that it is launched from. Either it's landing higher or lower than where it is launched from. So, when we try and solve something like this, our time is the tricky part because our time to the top and our time to the bottom, or time up and time down, are not the same. Let's take a look at an example and see what we can figure out. In this case, we have a cannon on a cannon with a cannonball with a velocity of this, which is our VI, at an angle of 40 degrees, that's our theta. And we're asking how much further could that cannon shoot if it was placed on a 30-meter tall hill. There's a bunch of things. Notice that this is how much further. By further, we're saying the distance that it's launching on level ground is going to be less, or we're implying that it's going to be less than the distance if it's launching from a hill. And we're trying to figure out the difference in those distances. So drawing a little diagram of this here, what I've got in the first case, I've got a cannon and it's launching a projectile like that, where it's got a VI like that. In the second case, I have a hill and the cannon is on top of this hill and it's launching a projectile with a VI like that, but it is 30 meters higher. How can I solve these? Well, let's start by this solution here. So on the flat ground. Our first step is I need to decompose the initial velocity here. So I'm going to do decompose. Decomposing these means I'm going to go my initial vertical velocity is 340 sine 40. So my initial vertical velocity works out to 218.5478 meters per second. Hooray for decimal places. My horizontal velocity is 340 cos 40, which works out to 260.4551 meters per second. Okay, good. Step number 2. I need to figure out my vertical parts. Here's what I know. My up and my down are the same in this case because I'm approaching the same, so I'm landing at the same height as I'm launching from. In this case, I can use delta V equals AT, and I know that my delta V is negative 218.5478 because I'm slowing down from this to 0. I know my gravity, looking for time. This is the time to go up. So my T up works out to 22.2781 seconds. My total time is 2 times T up because we are at the same height. So that just works out to 44.5561 seconds. And I'm leaving my numbers in my calculator and going from there. All right. Next, I need to figure out my horizontal. So my third step is to figure out the horizontal part. I have my horizontal velocity. I know that my horizontal distance is that horizontal velocity times my total time. So that works out to 260.4551 times 44.5561. And that works out to 11,604.87 meters, which is 11.6 kilometers. That's a long way. Okay, great. This is landing at the same height. So this is for this first option here where we're landing at the same height as we're launching from. Let's take a look at the second option. This is the one that gets a little bit more complicated. We've done this first one in the last video. For our second option here, what we're looking at is we have our vertical and horizontal components already. So I'm actually just going to take those like this, and I'm just going to reuse them. This may not always be the case. You may not have to do this part first, but I've already done them, so I'm just going to reuse them. Now notice my T up is going to be the same as when I'm not on a hill. So my T up is going to be 22.2781 seconds. I have the same cannon, firing the same cannonball at the same velocity from the top of the hill. The time it takes to go from here to here, this is my T up. In this case, the time it takes to go from there to the apex of this is going to be exactly the same. It's the same cannon, the same cannonball, the same initial velocity, all that sort of stuff. The part that is not going to be the same is going to be this down part here. So my time down is going to be quite a bit different. How do I solve that? Well, kind of interestingly, I'm not actually interested. I need to find out how far it falls. I can figure out what my vertical velocity is. It's 0 at the top there, but I need to just know how far down does it have to go from the top of that arc. I'm higher than 30 meters. So I'm higher than the 30 meters because it went up. How far does it fall down here? So if I fall all the way down, can I figure that out? Well, the way that I can do that is by figuring out how far did I go up. How far did it go up during this first part? Or in other words, what is the distance up? I think the easiest way to solve that is use VF squared equals VI squared plus 2AD, that formula. And I can start plugging things in. I know that's 0 because it's at the top of the arc. This is 218.5478 plus 2 times negative 9.81 times D. There we go, I'm running out of space. So my D up is, solving all that out, I get 2434.4106 meters. So that's how high I went above my initial launch. However, I have to fall down an additional 30 meters. So I'm going to go 2434.4106 plus the additional 30 meters of the hill, which works out to 2464.4106 meters. Okay, that's useful because now I can do the distance down is half times my vertical acceleration times t squared, and this is the t down. And now I can say I found out how far it has to fall down. I know my acceleration. How long does it take? 2464.4106 equals half times negative 9.81 times t down squared. So my solving this out, my time it takes to fall down from the arc, from the top of the arc, works out to 22.4149 seconds, which is close, but not the same as the time it takes to go up. Notice these are not the same. They're close, though. So my total time works out to 22.2781 plus 22.4149, which works out to 44.6930 seconds. So if I look, and again, just a comparison, notice that the cannonball is in the air for slightly longer when it's launched from the top of the hill as opposed to being launched from the flat ground. This here is where the complexity comes in. All of this stuff here, finding the T up and then figuring out my D up, my D down, my T down, is finding out the vertical components here. So the vertical component, when you're launching and landing at a separate height, the vertical component gets much more complicated. I have to do both my time up and my distance up, and my distance down and my time down. And I have to figure out all of those in order to figure out the total time, because this total time here is what we're trying to figure out. Now I can use that to come to my horizontal part, and that's really easy. DH equals VH times T total. Plugging that in, I get 260.4551 times 44.6930. And my horizontal distance that was traveled, in this case, works out to 11640.51 meters. So this is from the hill. This here is from the flat ground. Notice it went a little bit further on the hill. However, we're not quite done because the question actually asks how much further. So it's worth always going back and reading the question. How much further does it go? Well, I'm going to use this space here. And I'm just going to go subtract the big one minus the small one. 5,1, subtract 11604.87. And that works out to 35.64 meters further. So this here is my very last step in this box here, figuring out how much further it went on the hill. Now this question is a little bit more complicated because I have to compare two of them. I have to compare the flat with the hill. However, if I was doing this for just on the hill, I'd still need to decompose. I'd still need to find the T up, and this is where it would change. I would not find my T total like this. I would now go from this T up to here, figure my D up, figure my D down, figure my T down, then my T total, and then I can go to the horizontal, which is actually the same step for both of them. My vertical stuff here gets more complicated if I'm on a hill. This is worth making notes on. When you're looking at solving a projectile motion problem, how you solve it, how you figure this out, actually becomes a little bit more complicated, and it's worth writing it down. Write down the steps, decompose it, find your vertical component. What do you need to do to find that? Find your horizontal component. That's the really easy step. Okay? I hope this has been helpful. In our next video, we're going to take a look at modeling this using software to sort of graph out what's going on with our vertical component, because that's worth checking out and worth taking a look at. Hope you've had a great day, and I'll see you later.